Okay, so this is going to be old school video style. I would like you to go ahead and take your notes, and just from your warm-up, you're going to, in this section right here, review what it means to think about probability regarding a bag full of marbles. What I'm going to ask you to do a couple times during this process is to pause the video and to really work through and think through some of what these are asking. A lot of it's just going to be review for you. So give it a shot. And if you would for me, read through these. And when you're ready, unpause the video. Okay, so here we're asking, what is the probability that you draw 3 red marbles in a row? So the way we think about this is every single draw is independent. The probability of drawing a red in the first option is 7 out of 10. The second option, 7 out of 10. And the third option, 7 out of 10. And when we talk about that, we're going to reference it as the probability of, in this case, 3 red. So P being probability, and then what we want the probability of happening inside the parentheses. And when you crank out those numbers, you're going to get 0.343 as a probability. And number 2, what's the probability that you draw 2 green marbles in a row? Well, that's going to depend on your number of green, which in this case is 3 out of 10. As a reminder, in this situation of probability, we multiply the probability of each. This also is 3/10. So when we get our calculators out, if you haven't already, go ahead and do that. This is 0.09. So the next one is where things get a little more interesting and where it's going to start to tie in with what we've been doing over the past couple days. We're going to draw 4 marbles, but we want the probability that exactly 3 of them are red. So it would make sense if all of a sudden we said, okay, well, that's fine. We'll just attach it to what we just did. We want a red, a red, a red, and a green. This probability is 0.1029. But if you really think that through, that should bother you just a bit, because it doesn't clarify when the 3 red have to occur. So in truth, it could be that the first one's red and the second one's red, but maybe the third one is green and then the last one is red. Still fits the actual probability that we're talking about. So we now have another 0.1029. But as you can tell, that green could really occur at any time. So it could also occur here. So we've got a red, a green, a red, and a green. Now the truth is, whoops, sorry, my fault. A red, a green, a red, and a red. This probability remains the same, right? If I'm doing the multiplication, the order doesn't matter. So even in the last one, where the green could be here, and then that's a 3, by the way. And then this is 3/10, 7/10, 7/10, and 7/10. This gives me 0.1029. But the question then is, what do I do with those? And I go ahead and I state that the probability of 3 out of 4 are red is the sum of all of these. You end up with approximately 0.412 as a probability. So if you would for me, keeping this in mind, what I'd ask you to do is think about the idea of rolling a dice. Sorry, 2 dice. I have different outcomes, and the sample space of those possible outcomes are listed here. If I roll 2 dice, I could have a 1 and a 1, a 1 and a 2. Technically, I could have a 2 and a 1 if I'm looking at them in order of how the 2 dice appear. I could have a 3 and a 1, a 2, 2, 1 and 3. You get the idea. All 36 of my options for rolling 2 dice are listed there. We talk about what's happening with the roll of 2 dice by listing them as events over to the side. So we could, for example, roll doubles. That would be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc. We could roll 2 evens. So I would look for 2, 2, or 2, 4, or 2, 6. You could find those here. But we're going to start to actually talk about the sum of the 2 dice. Now, as a quick reminder, this may seem inherently obvious, but just in case it's not, the sum can never be lower than 2, right? If I'm always rolling 2 and the lowest I can have is 1, then the lowest sum I could have is 2. All of my possible sums are listed here. But I want to talk for a minute about what this chart represents, and then we're going to show you where these numbers are coming from. What this is going to talk about is referred to as a probability distribution, where I want to know what my possible options are. A sum of 2, a sum of 3, all the way up to 12. And when I talk about those, I then need to isolate each individual option. So, for example, in my sample space of 36, what is the probability that I roll a 2, a sum of 2? Well, just by looking, I can see, okay, well, there's really only one option, right? I would have to roll a 1, 1. So that would be an obvious 1 out of 36. But let's also talk for a second where else that comes from. It also comes from the idea that I have to roll a 1 and a 1. So I have 1/6 of an option for the first dice and a 1/6 of the option for the second dice. Another way to get 1/36. Well, you're going to start to see some patterns here. What if we talk about rolling a 3? If I roll a 3, you might say, okay, well, that's just easy. I look up at the sample space and just count them up. The answer is 2 out of 36. And so for those of you who, haven't gotten your calculator out, get your calculator out. And when I do 2 divided by 36, I'm going to get this decimal. But the other question then should be, well, what if I didn't have this whole list? Well, what adds up to be a 3? I would need to roll a 2 and a 1, or I could roll a 1 and then a 2. Well, what's the probability of rolling a 2? 1/6, 1/6. Probability of rolling this, 1/6, 1/6. I have a probability of rolling a 2 as 1/6, the probability of rolling a 1 as 1/6. That option is 1/36, but I have this option as well, also 1/36, the total being 2/36. Now, this process just keeps going, right? If I want to talk about what's the probability of rolling a 4, yes, I can go up here and I can say, okay, here we go, 1, 2, 3, those are my options. Or you could go through a similar process here. Roll a 3 and a 1 and a 3, a 2 and a 2, and you're going to get that 3/36. So what you see in just this slide here is this idea that we are going to talk about several things. We're going to talk about what are my options, my sample space, what's the probability of any one of these sample spaces occurring, and then we're going to create these charts. The chart will be the set of options that you could get from our actual experiment and the probability that each of them happens. Okay, so go ahead and turn the page and look now at this experiment. We're going to flip 4 coins. And the outcomes are going to be whatever my coin ends up with. Might be head, 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 or tail, 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 tail. Our job is going to be to create a probability distribution that also includes the other options. What if I have 3 heads and a tail, or tail, head, tail, head? So we're going to talk about, okay, what does my probability distribution chart look like? I could have 0 heads. Well, just by glancing up here, there are a couple things we want to notice. First of all, in order to talk about that probability, sorry about the movement there, in order to talk about that probability, we need our sample space. Well, we've got 16 options in our sample space. So quick probability, we just say, oh, okay, well, this is just a nice and simple 1/16, which seems like that's done. And it is in a way. I mean, I can go ahead and put in here, this is 0.0625, no different than if I said, hey, what's the probability of getting 4 heads? Done. 1/16. But what you always, and let's go ahead, sorry, and put this decimal, 0.0625. But what we always want to be thinking about is also this idea that where is this 16 coming from? Well, I have 2 options for the first flip, 2 options for the second, 2 options for the third, and 2 options for the fourth. Just by quick 1, 2, 3, 4, that is going to be 2, 4, 8, 16. Remember, I multiply for my total number of options, so that would give me 16 options. But another way to think about this 1/16 is if I want 0 heads, what's the probability of flipping a head? 1/2. or tail, sorry, of a tail, 1/2. Tail, 1/2. Tail, 1/2. This would be tail, 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 tail. 1/2 for the tail, 1/2, 1/2, 1/2. What's that give me? 1/16. Now you may be like, wait a minute, can't I use that exact same rationale for 4 heads? Absolutely. Head, 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 head. Probability of a head, 1/2, 1/2, 1/2, 1/2. That's 1/16. But these 3 interior ones get tricky because what happens is I end up saying, oh, okay, I want to talk about 1 head. Well, if I look up at the table, there's 1 head there and 1 head there. There's 1 head there and there's 1 head there. Now listen, because this is where this is going to get more important. Up here, there was 1 combination of 1/16. Up here, for 4 heads, there was 1 combination of 1/16. But here's where this should start to sound familiar. Notice we're flipping 4 coins. This was 1. This is now, if I think about wanting 3 heads, I have a probability for the first, second, third, and fourth. I want 3 of them to be heads. Well, what's the probability? 1/2 that the first is head, 1/2 that the second is head, 1/2 that the third is head, and 1/2 that the fourth is a tail. But I know that there are 4 combinations of those, 4 sets of 1/16. So I have 1 set of 1/16, 4 sets of 1/16. As a decimal, this is 0.25. But hopefully you can tell where we're headed. Guess how many sets of 1/16 there will be here. If you are seeing that this is 4 coins, 1, 4, and you've heard me say this line now multiple times. How many sets of 2 are there? There's 1, 2, 3, 4, 5, and 6. There are 6 sets of 1/16. This decimal is 0.325. 1, 4, 6. You shouldn't have to count this time. It's not a coincidence. There are 4 sets of 1/16 here. That's 0.25, and 1 set of 1/16 there. This idea is referred to as a binomial probability. So for a minute, if you would, for me, flip to this page. Again, super old school because I'm literally flipping. On this slide right here, it talks about this idea of independent repetitions of a trial, and here's the key. The word binomial we've talked about is in reference to 2. We have, in these situations, we have 2 possible outcomes. One is the success of what we want. One is a failure of the opposite, what we don't want. And the probability that those together will occur is 1. And this should look familiar because what this is telling us is that the probability distribution is based off the rows of Pascal's triangle. So we're going to look at this in 2 more examples and then I'll be done. If you go back to the bag of marbles, we look again at 7 red and 3 green. And we've got options to draw 4. Here is my sample space. Why? For the exact same reason that it was before. But notice that these decimals are not the same. Why not? Well, because when it was just a head and a tail, it was an even probability. It was 1/2 for a head and 1/2 for a tail. But the probability of a red here is 7/10, and a green is 3/10. So on the next slide, we're going to address where these numbers come from, and it's going to go like this. This is our sample space off to the side, and when we're done, if you want to pause just to count them up, I think that would be helpful. We're going to create and show that this probability distribution is the probability of pulling 0 reds, 1 red, 2 reds, 3 reds, and 4 reds. Why are we specifically talking about reds? Because right here it says that our event, X, is the number of reds drawn. Inside, the notation, probability of 0 reds, 1 red, 2 red, 3 red, 4 reds. So what we're going to now do is say, okay, I want to know the probability of getting 0. Well, the way this is going to work is this is going to be just like combinations. There will be 4 choose 0 of whatever our probability is. You should guess where this is going. This is 4 choose 1. This is 4 choose 2. This is 4 choose 3. And this is 4 choose 4. What are these numbers? There will be 1 set, 4 sets, 6 sets, 4 set, and 1 set. 1 set of what might be what you're asking. Well, I want there, in this case, to be 0 reds. So, fine. I've got a probability for 4 draws. What's the probability of a not red? 3/10, 3/10, 3/10, and 3/10. When I multiply that all out, I have 1 times 3/10 to the 4th. That's 0.008. That's what's down here on the chart. Then I want to talk about the probability of pulling 1. Now after this one, I want you to turn off the video, hit pause, and try the next 3. What's the probability of just pulling 1? Well, for the record, I could list the probability just the way we did on the front. Probability of 1 would mean that the first one, for example, could be 7/10 because I pull a red. There's a 7/10 probability of pulling a red. Then 3/10, 3/10, 3/10 for pulling green, green, green. But the deal is, how many different places could this one red be in? Well, it could be in this spot here, this spot here, that spot there, and that spot there. There are 4 options for this probability. If you're not confident in that, count them up. Come over here and count how many times 1 red occurs. It will occur 4 times. Well, what is this? This is 4 times the probability of what I want once times the probability of what I don't want. Sorry about that. 3 times. When I do this, these powers in our calculator, you know, the one you already got out, Jack Krause, when I put these in here, this will give me my 0.076. Okay. So now I'm going to go through here and do this for the 6, for the 4, and for the 1. So what I want you to do is hit pause and see if you can come up with what would my probabilities be here and what would it look like if I simplified it over here. Go ahead and hit pause and then check it when you're done. Okay, so what you want to now look at is we've got a probability of just having 2. 1, 2, 3, 4. 2 reds would look like 7/10, 7/10. 2 green would be 3/10, 3/10. I have 6 sets of 2 of what I want and 2 of what I don't. This, when you do this multiplication, you get 0.265 for 4. Hopefully we're getting the hang of this now. This is 7/10, 7/10, 7/10, and 3/10. I should have said for 3 reds, sorry. There are 4 sets of this combination. That would be 4 sets of 3 of what I want and 1 of what I don't. Last one, this would be 7/10 to the 4th. The sum of these, as you add those up real quickly, that should always be at 1 because the probability of all these happening will total 1. The idea behind this is that if I take combinations, remember this is both the Pascal triangle and the notation for combinations. The combinations of these probabilities, the sum of them will be 1 and will give me the probability distribution. So the last one we just want to do together, and then we'll swing back around on Monday and really sum up this together when I am back, is an idea that sounds a lot more realistic, like what we're used to. And this is when you ask, is this used in real life? This is one of those sample types of situations. Over the course of his career in the NBA, Kobe Bryant has made 83.78% of his free throw attempts. If Kobe were to attempt 10 free throws, what is the probability he makes exactly 8? Well, essentially it's like referencing back here this idea of reds and greens. But in this case, we're going to specifically clarify that what I want is to say, okay, fine, I want 8. Well, then that's the idea of, hey, I am in the 10th row of Pascal's triangle, and I want the 8th element. That's saying, hey, listen, if I were to talk about this, and I were to say he had an 83.78% chance of making his free throw, well, I want him to make 8 of them. Now, in reality, he's going to then miss 2. What would this probability of him missing be? Well, hopefully this makes quick and easy sense. That if his probability of making it is about 83, then his probability of missing would be about 17. So if you do that quick math, that's 1 minus 0.8378. This would give me 0.1622. His probability of making 8 looks like this. Missing 2 looks like this. But remember, those could come in any combination. So the 2 that he missed could be the first 2, it could be the middle 2, it could be the first and the 7th. It doesn't matter. How many options will there be of 10 choose 8? Well, if you take 10 choose 8, you can go back onto your, sorry about that, you can go back to your Pascal's triangle, find that number, or really quickly plug that into your calculator. Then do 0.8378 to the 8th, 0.1622 to the 2nd. And when you do that, you will get that his probability of making exactly 8 is 0.287. So that is all you have to actually do for the homework. So we're going to do one more that sounds like it, but I want you to go ahead and hit pause. And if you would for me, try number 2. What's his probability that he makes exactly 2? Okay, so the last one here, we're going to use the exact same process. We're going to say, hey, listen, his probability of making it is 0.8378. How many times? Twice. What's his probability of not making it? 0.1622. How many of those? 8 of them. Well, when do those 2 have to occur? It doesn't matter. Anywhere within the 10. So what that means is, hey, he takes 10 shots, any 2 of them he needs to make. If you do that, if you run that math, you may have found something that said 1.51 times 10 to the negative 5th. That's just an interesting stat. That says the likelihood that he makes exactly 2 is near 0. So that is the end of this new content. Don't panic if it doesn't totally make sense, but there hopefully is enough here that you should be able to give it a shot. Your homework worksheet is also on the shelf. Make sure that you get that, but you don't have to do all of them. So check Schoology or listen to what the sub said because they're going to walk through exactly which ones you have to do. So just certain ones, mostly the A's, and then there's a B in there as well. So just make sure you check Schoology. Also make sure you check Schoology to be sure that you have everything ready to be talked through on Monday as well. So you got several things you want to make sure that you're ready to go with. I hope you have a great weekend. Thanks for listening.